going to try this video out one more time. This is our first chapter 3 video covering sections 1, 2, and 3. So starting with the introduction here, it's telling us that we have 91 elements in nature and 118 total, and we can combine those in many different ways to create compounds. When we do combine them to make compounds, they lose their individual properties. So what that means is, here's our hydrogen. It is a gas at room temperature. It's explosive. Oxygen, same story, gas at room temperature. It's required in order for us to have fire. But if we put these two together, they lose their individual properties when we make water. Water is a liquid at room temperature, and instead of creating fire, it's used to extinguish fire. So those individual hydrogen and oxygen properties are no longer present. In order to talk about compounds and the elements that they contain, we have to be able to recognize those elements and how many there are in each structure. So this equation says, this problem says, determine the number of each type of atom in each formula. So here's our first formula, CuSO4. So when we're trying to decide which elements are in this formula, we're looking at capital letters. So every time we see a capital letter, that's a new element. If it's a capital letter with a lowercase letter, that's representing one element. So we have Cu, which is copper, S for sulfur, and O for oxygen. To decide how many there are, we're looking at their subscripts. Now, if you don't see a subscript, that means that there's one of them. It's an implied number. So there's one copper and one sulfur and 4 oxygens. So same story down here. We look at what our compound contains. We have magnesium, hydrogen, carbon, and oxygen. And when we look at the amounts, there's 1 magnesium. To decide how many there are of the 3 other elements, we have to notice that they're in parentheses and there's a 2 outside of that parentheses. So there's 2 of this whole group. So whatever our subscript is, we're going to multiply that by 2. So 1 times 2 gives us 2 hydrogen, 1 times 2 gives us 2 carbon, and 3 times 2, 6 oxygens. Our compounds are held together by chemical bonds. Chemical bonds are attractions between positives and negatives. There's different ways to form those attractions and to form those charges, though. The 2 main types are ionic and covalent. We're going to look at those on the next slide. This is showing us a couple representations, though. The line between the atoms represents the chemical bond. That represents what's holding those atoms together. And in this one, the space-filling model, the atoms are just kind of squished together. That's representing the bond. So we'll start with ionic bonds. In an ionic bond, an electron or electrons, one or more, have been transferred. So what that means is that our metal is going to lose an electron to form a cation. We talked about this in chapter 2. Now when it loses that electron, it doesn't just fly away into outer space. It has to give that electron to something. So it gives it to a nonmetal, and our nonmetal becomes an anion when it gains that electron. So the electron's been transferred from the metal to the nonmetal, creating 2 charged ions, a cation and an anion, and the attraction between those positive and negative charges gives us our ionic bond. A covalent bond is when 2 atoms share electrons. So the electrons are in between the 2 nuclei, and that's the attraction from each nucleus to the electrons. And we usually see these when nonmetals are bonded together. And down here on the bottom, the example of the most stable is right here. If we have an electron that is equally between the 2 nuclei, but as close together as possible, that's the best scenario. Here's another example of our ionic compound. So here's our sodium, metal. It's going to lose an electron to become a sodium cation. Now that electron that it loses, chlorine is going to gain that electron to become a chloride anion. When we put those two together, we make sodium chloride, or table salt, an ionic compound. Individually, sodium is a metal, it's shiny, it's explosive, you can cut it with a butter knife, it's very soft. Chlorine is a yellow poisonous gas that's really stinky. But when we put them together, we make table salt. So again, they've lost their individual properties and they've created something new. We do have a couple different ways to represent formulas. Down here on the bottom are 4 most common examples. The first one is the molecular formula. Now this one is good because it's showing us which elements are involved and how many of each, but that's it. The structural formula shows us which atoms are involved, how many of each, and it's also showing us how they're connected to each other. We will learn how to draw these in a later chapter. The ball and stick model is showing us the same thing as structural, but now in the actual 3D format. So it's a good representation, but it's difficult for us to draw, so we usually use computer modeling. And then the space filling model is the most accurate, but because it's kind of blobby, it can be hard to see all the atoms. They can get blocked. And again, we use computer modeling. So each of these have their own pros and cons, their own purposes, so we end up using all of them depending on what we're looking for. One of the last topics we're looking at is 2 different types of formulas, molecular formula and empirical formula. A molecular formula is the way that the molecule actually exists in nature. Its actual formula. Its empirical formula is the lowest ratio. So we have a couple examples here. The molecular formula of hydrogen peroxide is H2O2. We have our 2 oxygens in the middle and the 2 hydrogens on the outside. So they are in a 2:2 ratio. But we can reduce that down for the empirical formula to get that 1:1 ratio. Benzene has a formula of C6H6. So we have the 6 carbons, the 6 hydrogens. That can be reduced down to a ratio of 1:1. And then glucose, a type of sugar, has a formula of C6H12O6. And here's its structure. The carbons are the black in the center, where the red oxygens and the white hydrogens. All of these subscripts are divisible by 6. And that gives us an overall ratio of 1 carbon to 2 hydrogens to 1 oxygen. Alright, the last thing we're going to look at is one more problem. Write a chemical formula for each molecular model. See Appendix 2A for color codes. So this little chart down here is from Appendix 2A. It's showing us the color of these atoms, what they represent, and these are standard colors. So oxygen is always red, carbon's black, hydrogen's white. So really we're just matching up the colors and then determining how many there are. So in this first one we have a blue nitrogen and red oxygens. When we write out the formula, we put the subscripts after the element. So there's 1 nitrogen, remember 1's implied, so we don't need to write that, and 2 oxygens. So with this one, we have that big yellow atom, which is sulfur, and then the white hydrogens on the sides. So we have 1 sulfur, 2 hydrogens, we write it as SH2. And then in our last one, we have that black carbon in the center, surrounded by hydrogens. So when we write this out, we get CH4. Alright, that is it for this video. Thank you.